Now I want to spend some time talking about polar molecules. So we left off saying that we want to talk about intermolecular forces, and that intermolecular forces are all about the attraction between positive and negative charges. So where do those show up in molecules? So we know that every single molecule lacks an overall charge, except for polyatomic ions. But neutral molecules, which is what forms bulk phases, right? Water, ammonia, all these things, these molecules that we're going to be talking about that form, these sorts of bulk phases are always going to be neutral, right? Compounds are neutral. And so if you have an individual molecule, it's not charged. So how can we have attractions between two molecules that are based around charge? Well, the electrons in a molecule are not necessarily evenly distributed around the molecule. There are regions of slight charge that can form. Okay, this is called charge separation. And what this leads to is called a dipole, and it leads to molecules that are polar. So here I have kind of a 3D representation of a water molecule that has shaded red and blue regions. The red region around the O atom in a water molecule has a concentration of electrons. These are there's a slight bit of negative buildup, right? There's still a neutral molecule. There's just kind of a little more electrons around the oxygen atom than there are protons in the nucleus to counteract it, leading to a buildup of some negative charge. This is not ionic. We call it slightly negative. It's not like an electron's moved full on. It's not forming an anion or anything like that. But there's a slightly negative end of the molecule. At the same time, there has to be a slightly positive end of the molecule. So one of the things you'll notice that these are called dipoles. Di meaning two. There are two ends, a positive end and a negative end to a molecule. So molecules that are polar have these slightly positive and negative sides, and that's what's going to allow and drive these intermolecular forces interactions. So how do we determine if a molecule is polar? So polarity starts at the bond level. We know that two different atoms share electrons in a covalent bond. But electronegativity tells us that not every atom pulls equally on sharing those electrons. This is a periodic trend. We can arrange it. Fluorine in the top right on the periodic table does not form or has a really high electronegativity. It doesn't share electrons very well. It pulls them towards it. So for example, in a bond of HCl, we can see that chlorine over here is at electronegativity of 3, hydrogen's at 2, meaning that there's a little more negative charge on the chlorine side. Those electrons are spending more time. They're kind of shifted over towards the chlorine side. Those orbitals are kind of pulled towards the chlorine side of the atom. So when we're looking at individual bonds, that's where polarity starts. We would talk about bond polarity. And in terms of diagnosing bond polarity, if we want to have atoms with equal electronegativities, that would be the same atom. So in this case, two chlorine atoms. That will result in a nonpolar bond. They are literally sharing electrons. Both chlorines are pretty electronegative. They're pulling pretty hard, but if you imagine you have tug of war with two people that are equally strong, the electrons just don't shift, right? The orbitals stay balanced. The electrons are equally distributed between the two chlorine atoms. There's no positive end and there's no negative end. Atoms with different electronegativities would have a polar bond. Okay? For that, in order for atoms to have different electronegativities in a bond, they just have to be different atoms. You can go look on the chart and find some fringe cases of where there's two different atoms, same electronegativity. We're not going to worry about that. Two atoms that are the same, nonpolar. Two atoms that are different, polar. Okay? And so when we're talking about those poles, remember one is positive and one is negative. We can say that we have a slight positive end, a slight negative end. We can draw dipole moments pointing. We can predict which side is which side's negative. That's the more electronegative. And so there's more electrons around the chlorine. That's why the negative side is there. Okay, so what we know that that's going to be what's going on. That if it's the same atom, nonpolar bond, different atoms, polar bond. We can also start to see something that comes up is that the same atoms leads to an idea of symmetry. That is a symmetric bond. Different atoms that is asymmetric, that's where polarity comes in. So that was for bonds. What we care about are molecules. So if a molecule only has 2 atoms, you're done. But if the molecule has more than 2 atoms, it's a more complicated process to determine if that molecule is polar. Okay? You have to combine all of the different bonds. So let's look at an example of water, and we're going to work through, I'm going to talk about the whole kind of process. So it starts from the Lewis structure. Water as a Lewis structure, it's an oxygen atom with 2 lone pairs, and then a single bond to 2 different hydrogen atoms. And so this has a bent molecular shape. So this Lewis structure is also showing the shape of the atom or the molecule. That's really how the atoms are arranged relative to each other. We know that each bond is polar because oxygen and hydrogen are different. So each bond is polar. And we know that the bond dipoles would point towards the oxygen. Okay. So when we want to combine those, we add them as vectors. So you can think about these as ropes that are getting tugged, right? That's what it means to add something as a vector. And you can see that these are getting pulled both in. So functionally, they're canceling each other out. You're pulling to the right and you're pulling to the left. That does not yield any net change, right? Because you're pulling equally. So you pull left, pull the right, nothing happens. But in the case of the vertical, you pull up in both directions. And so you would see a net shift up. These would combine with each other. And so you would say that there is an overall molecular dipole. Water is a polar molecule. If there's one thing you remember and take away from this, water is polar. This is going to be really useful over the next few weeks. The fact that water is polar is going to come up again and again. So water is polar, and that's because the bonds are polar, but it also depends on the shape of the molecule. Because there's that bent shape to the molecule and the fact that the bonds are polar means we end up with this negative side or positive side of the molecule where the hydrogens are. And we also end up with this negative side of the molecule where the oxygens are. This is, remember, the dipole. We have to have a positive side and a negative side. If we look at, for example, something like carbon dioxide on the left, those bonds are still polar. Carbon and oxygen, different atoms. But the problem is, if we look at the ends of the molecule, that's a negative end of the molecule, and that's a negative end of the molecule. That is not a dipole. There's not a positive side and a negative side. So when we're determining whether or not a molecule is polar, it's not just are the bonds polar, but does the shape of the molecule lead to a situation where those polar bonds combine to give you a positive side and a negative side of the molecule. So coming up with those shapes can be a bit tedious, maybe a little bit, you got to kind of dust off a little bit of cobwebs on those, but we can also just kind of take these ideas about symmetry and about canceling out and come up with some guidance as to what sorts of molecules are polar or not polar based off looking at their Lewis structure. So as long as your central atom obeys the octet rule, a small molecule, so you have an acentered atom, is nonpolar if there are no lone pairs on the central atom and all outer atoms are the same. Okay, so when it was just 2 atoms in the molecule, we just looked at are they the same or are they different, like HCl was. But in this case, we can just look at are there no lone pairs in the central atom and all outer atoms are the same. Both of those must be true in order for a molecule to be nonpolar. Let's look at some examples. I have NH3 and CH4. And I want to determine if each of these molecules is polar or nonpolar. So I could start off, draw the Lewis structure. As we move forward, if we want to know properties of molecules, drawing the Lewis structure is going to be our best first bet where we always want to jump off from. What's the molecular shape of the molecule? Are the bonds polar? Do the bond dipoles add up to give the molecule an overall dipole? This is what I walked through with the oxygen example. Requires, a lot of steps, or we could just kind of short circuit it. After we draw the Lewis structure, we could instead just say, are there lone pairs on the central atom? Are the overall atoms the same? One of the things is that this kind of longer route out here does let you know which side is positive and which side is negative of the molecule. This will only tell you, is the molecule polar or not? It's an easier process, so you don't get as much information. Sometimes we don't need to know which side is positive and which side is negative. We just need to know, is it polar? And you'll note that's all this question asked. And so if that's all you need to know, you can just stop right there. And you need to have no lone pairs on the central atom, and all the outer atoms have to be the same in order to be nonpolar. Otherwise, the molecule has to be a polar molecule. So let's take a look at NH3 and CH4. Got my Lewis structures. So I know NH3, I can see I have a lone pair on my nitrogen atom, and then I have the three single bonds out to the hydrogen atoms. Once I see that lone pair, there's a lone pair on the central atom. And so that means this is a polar molecule. I'm done. As long as I have a lone pair on that central end, this is a polar molecule. No lone pairs on the central atom of methane, which is good. We also now want to check whether or not the outer atoms are the same. So if I'm looking, I can see I got hydrogen, 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 hydrogen. Those are all the same. So I do need both of those to check off. No lone pair central atom, outer atom's the same, nonpolar molecule. Okay. Once I check off both of those, if either of those fails, it's a polar molecule. We can understand this by looking at the three-dimensional structures of the molecules. When we're talking about nonpolar, these kind of ideas of having no lone pair central atom, all outer atoms the same, really what's going on is we're saying this idea of symmetry is coming back up. In order for a molecule to be nonpolar, we have to be symmetric. Almost every single bond is polar because there's a lot of different atom bonds. But this molecule has this one going up, this one's going down and back, down and forward, down and to the other side. And so they're all pulling, but they're pulling in opposite directions and they cancel out. And that's what makes it a nonpolar molecule. On the ammonia, the NH3, what's driving this shape is that lone pair. We don't show it in the three-dimensional structure, but it's taking up space on top of that nitrogen. It forces those hydrogen atoms to all point down. Since they're all pointing down, the bond dipoles are all going to point up towards the nitrogen. They're not going to point side to side, or they're all pointing side to side, but those cancel out. But that vertical component doesn't cancel out, and that's why your ammonia is a polar molecule. So these dipole-dipole interactions are what are going to be one of the main driving forces of how molecules interact in the bulk phase. Because molecules if they have positive ends and negative ends, those are positive and negative charges that are going to interact with each other. These dipoles are always there, and like charges repel each other, opposites attract. Molecules are going to arrange such that you kind of minimize the repulsive interactions and maximize all the attractions. And so this is really one of the biggest, most important factors about dipoles, because that's how molecules interact with each other, is via those charges. And if there's just a positive end and a negative end, they're going to interact with each other. And so we'll pick more up, delve more into that idea in a future as we move forward. Just want to introduce this idea, review a bit about polar molecules, because it's going to be important. All right, that is another video down. There's just one more in this set of videos to get us started on chapter 10 here. See you there.